Hello friends, good morning. So far in this series, I have explained what is Townsend's experiment, what are the different breakdown mechanisms in gaseous dielectric, what is Townsend's current growth equation, what is Townsend's breakdown criteria, and then I have taken numericals on Townsend's breakdown criteria. Today, first I will explain what are the limitations of Townsend's breakdown criteria. The first limitation is it is applicable when gas is at low pressure. That's why we have kept the gas at low pressure in the Townsend's experiment. Number two, the breakdown voltage in practice depends on the shape of the electrode, that is electrode geometry. Townsend's mechanism do not explain the effect of electrode geometry on the breakdown. Number three, the Townsend's criteria predicts the time of 10 to the power minus 5 seconds, minimum time of 10 to the power minus 5 seconds for the breakdown. Whereas in actual practice, breakdown can occur in time less than 10 to the power minus 5 seconds, and it is observed that the breakdown can occur in time 10 to the power minus 8 seconds also. And fourth, Townsend's criteria predicts very diffuse form of the discharge, but in actual practice, the discharges are of filamentary nature also. So there is another theory which overcomes all these limitations of the Townsend's breakdown criteria, and that theory is called as Stimmer's theory of breakdown in gaseous dielectrics. I will explain this theory by means of these three diagrams. The first diagram. Recall the Townsend's experiment. There were two electrodes, cathode and anode. Anode is subjected to voltage. Spacing is D, so electric field is V by D. When there is radiation on the cathode, an electron is ejected from the cathode and it moves towards the anode. In the process, it collides with the gas molecules, and if its kinetic energy is more than the ionization potential of the gas molecule, then there is breakdown and we get additional electron and the positive ion. So let us assume that its kinetic energy is more than the ionization potential of the gas molecule. So as we move from cathode to anode, number of electrons and positive ions will go on increasing. These electrons, if you observe, that is called as electron avalanche, because there is more number of electrons, so it is electron avalanche. So when electron avalanche reaches the anode, the positive charges are virtually at their position. The reason is electrons are very light, therefore they move very fast. Positive ions are heavy, therefore they move very slow. So these positive ions will form the space charge between anode and cathode. At present, the electric field is V by T. Now come to the second diagram. Here, lot of positive ions are there. Electrons are also coming continuously. So there will be photoionization. So due to this photoionization also, more positive ions will be formed. So the space between this anode, space across this anode will be completely filled with the positive ions. So if we observe the virtual distance between this cathode and this space charges, that has reduced to D dash. So electric field V upon D dash, that will be more than the original electric field. So ionization process will accelerate. So from these positive ions, a streamer will move towards the cathode and it will hit the cathode at some point. So due to this, a cathode spot is formed, and from this spot, electron beam will be ejected and it will move towards the anode, and it will, so here we will get the positive ions as well as electrons. So this is the conducting channel, and finally the breakdown takes place. So that is the Stimmer theory of breakdown. It takes care of all the limitations of the Townsend's breakdown criteria. Thank you.